All right, so now we move on to rational exponents. So at this point, we've dealt with rational bases, meaning let's say I considered I have some a over b, and it was raised to, let's say, an exponent of 2. We've dealt with lots of problems like this where the base was rational, but now what if we deal with an exponent that's rational, meaning what if I have x to the, let's say, 1/2? How do I deal with problems like this? And how can we use all the rules we've learned to this point to deal with exponents that are rational like this? All right, so we know that a rational exponent is anything that has a rational number. Well, what is rational numbers? Rational numbers, we remind ourselves, is something that can be written in terms of a fraction of a over b, where a and b are integers. And integers, we know, are any number like -3, -2, -1, 0, 1, 2, 3, and of course these extend all the way to infinity. It's the positive and whole numbers that extend in both directions here. Okay, well, let's consider the following, and we'll try and connect it to what we've done before. The product rule stated that if we have two things with a common base, we add their exponents. So we look at the example below and we say, okay, we have a common base of 5. I add 1/2 and 1/2, and that will give me 5 to the 1 power, because 1/2 plus 1/2 gives me 5 to the 1. We're going to learn today that we actually can write these in an equivalent radical form. And that's saying, okay, well, if I have exponential form, how can it relocate into radical form, which is something we did a lot in number sense, actually. So these things are equivalent forms, and we're going to show that a lot today. And in the example here, number 3, they basically confirm that, yes, we can take something that's in terms of exponential and make it equal to something in terms of radical form. Now, I think it's directly important to just go right to the examples in these cases, because we may look at this and understand, okay, well, we know that this is product rule and we know something's happening with the radicals here from our radical unit, but let's see if we can actually show through examples that we can combine all the knowledge we've learned to this point of not only radicals from number sense, but then exponent knowledge, which is the power, quotient, and product rule. So let's take a look. Before we get into that, what I'm going to have you do is I want you to consider the following here. In general form, well, I have something in terms of exponential form. So I have something in terms of exponentials, and it can be written as x to the power of 1 over n. Now, in terms of a number that we have here, well, we just on the previous page said, what if I give you a rational that's also in exponential? And so we're going to compare those two. And then on this other side, or the right side, we have a radical form. And we claim that these are equal even with some form of rational number here. Okay, one thing I would like you to add here is that our n value is always symbolic of our index. That's our index value of our radical here. And then our m value is going to be our exponent. So we have our exponent value, which is the m. We have our index, which is the n, or the part that's attached to our radical on the outside. And we can move from exponential into radical. All right, let's try an example here. And I'm going to try and clearly explain this to you. So we have a number 25. If they give us a base value, what I would always do is write out our radical symbol, write out the base below, and now we have to assign our rational number, or each piece of the rational number, into a piece of the radical. Well, what I want you to know is that our denominator is always the index value. So in this case, 2 is going to be the number we attach to the index on the outside of the radical here. And our exponent value, the exponent value always comes from our numerator. In this case, it is 1. Now, there's an equivalent way to write this. From above, we know we can say the square root of 25 and put it all to the power of 1 on the outside. That is also equivalent. So if we want to do 25 to the power of 1, then square it, or we want to do square root of 25 to the power afterwards, that would be fine. Well, what is the square root of 25? Simply, it's equal to 5. All right, we look at our second example here. Remember, I want you to always start with the radical symbol and whatever the base value is. Now we want to assign our denominator as the index on the outside and our power as the power or the exponent on the base number. This can also be written as the cube root of 64 to the first power. Well, the cube root of 64, that's going to be equal to 4. So in these first two examples, we could actually directly evaluate a specific number or a specific value. But going forward, we might not always be able to do that. Sometimes it's just going to be about reducing these as much as we can or converting them directly if that's what they ask for. So really depends on the problem. Some of them are just going to say convert from exponential to radicals or radicals to exponentials. Some of them will say give me a value. It's really going to depend on the problem. All right, in our next problem, we square root, or we put the radical and our base value. Our denominator of our rational exponent goes to the index. Our exponent goes within or outside. In t to the 1 over 3, same thing, we're going to write our radical symbol, t. Our index value is always going to be our denominator of our rational, and then to the power of 1. And of course, what we could do is we could rewrite both these as square root of x all to the power of 1, or equal to cube root of t all to the power of 1. That would be the exact same thing here. Okay, we scroll down here, we look at e. This might be one we can directly solve or get a direct value from. So this is equal to, you always want to start by doing the radical symbol and your base value. And then you want to assign the denominator as your index value, the 2 or the numerator as your exponent. I could write this out as a separate way of saying cube root of 8 to the power of 2 on the outside. That's also an equivalent form. And this is equal to, well, I could either do it as 8 squared, which is going to be 64, cube rooted, which is 4. Or I can say, what's the cube root of 8? That's equal to 2. What's 2 squared? 2 squared is equal to 4. So whether we do the radical piece first or we do the exponent first, you'll see you'll get the same value. Now, I'm going to be more direct on this second example and see if we can show directly both ways that we get the same solution. So actually, even what I'll do is I'm going to backpedal here, and I want to show both ways can give you the same result even in this first one, because I think it's really important to see. So let's say I cube root whatever 8 squared is. Well, 8 squared is 64. The cube root of 64 is equal to 4. Now to show my secondary way, I have the cube root of 8 all raised to the power of that exponent or the numerator. This is going to be equal to the cube root of 2, or the cube root of 8, which is 2, and 2 squared is equal to 4. So no matter which way you do it, the radical or the exponent first, you'll get the same solution. Let's do that same thing with the next example here. I write my radical symbol and the base. I assign my denominator here, my numerator as the power. That means this is going to be equal to 4 cubed is going to be 64. The square root of 64 is equal to 8. Now, to show it the alternative way, I have this equal to the square root of 4 all cubed. Well, the square root of 4 is equal to 2. Raised to the exponent of 3, well, that's equal to 8. So now we move over to example G here, and we have things in terms of a variable. I could write this in two ways. I first start by writing my radical. I assign my denominator to the index and my 5 or my numerator to the power. But I could also rewrite this as the fourth root of p all raised to the exponent of 5. And then similarly with h, I could do that exact same thing. I could do my radical with a, or whatever the base is, assign my denominator on the outside, my m to the power, or I could rewrite this as I can have n, or the nth root of a, raised to the exponent of the numerator, which in this case is m. So this one's not going to give us a direct value, but we can represent it in a couple ways. Now, I think it's important to go through a couple examples and really just highlight some key things you may see or may miss in the process of doing these problems. So let's just deal with a couple of the ones where we take an exponential form and convert it to radical. Well, let's say we were considering 3 here. I can write this as, well, we always want to start with our radical, and then I want to assign my denominator of the rational to the index and my power here. And remember, I can always write it as the cube root of 2 to the 5th power. So if I want to write the exponent with the number into the radical, that's fine. Or if I want to write it on the outside, it will give you the exact same value here. And let's do one more example here. What if I did 6 to the 3 over 2? Well, this is going to be equal to, I write my radical first, I assign the 2 on the outside here, or my denominator, and I put my power here. Or I can say the square root of 6 raised to the power of 3 on the outside. Both are equivalent forms here. Now let's work in the opposite direction. What if I gave you a radical and then I say make them into exponential? Well, this is, especially with number 7 here, I want to point this out. If nothing is written in the radical here, we've actually been writing it in this whole time just for the purposes of the demonstration, but if nothing's written here, we know that anytime we see a radical and some squared term underneath, it means we're always square rooting, so the square root of x squared is x. In this case, it is no different. If you don't see a number written there, we know that that number on the outside is 2. But it's not going to be written in most cases, in fact, almost all cases. Now, if I want to do these types of problems, I say this is equal to, I write my base, I start the rational number here, and I say, what goes in the denominator? It is always the index, or the fact that we're square rooting, it's a 2. And my exponent goes in the numerator. Okay. Now, or I should say the power, or exponent, whatever you want to say here. For part 9 here, or question 9, I write my base, I do a fraction symbol, and then I say, okay, my index, or the part outside of the radical, goes here in the denominator. My numerator is the power, which is 5 in this case. All right, let's choose one more example from here. What if we did 12? Nothing's written on the interior here. Well, if nothing's written as the power on a number, it's always 1. And I can actually say this is equal to the base value with a rational exponent. This is going to be the index in the denominator, the power in the numerator. So it is 10 to the 1 over 6. All right, now we're going to deal with some more applied examples. We want to take these exponentials and write them in radical form, but this time they have maybe 2 things within that are attached. So what we're going to do is we're going to say this is equal to, I'm going to take everything written in the brackets, write it out together, and put a radical symbol. We know that, well, actually what we should be doing first here is we recognize that there is a negative in the exponent. And the negative in the exponent might cause a little bit of tricks here. We know a negative in an exponent on an average question would be x to the negative, let's say 1. And what do we do with this? The base value is always relocated to the opposite location. So we're going to do the same principle here. We're not going to flip or do the reciprocal of the exponent. We're doing the reciprocal of the base. I have 1 over 5x to the positive 5 over 4. That means this is equal to 1 over the square root, or I shouldn't say the square root, I should just say the radical symbol 5x. And now we get to assign our denominator becomes the index, and our power becomes the piece out front here as the exponent. And it's all under the radical here. And remember, you could write this in another way. You could also say this is equal to 1 over, and then the 4th root with 5x, and this is all surrounded by a 5, or to the 5th power. So either way is correct here. So if you have a negative, it's not that you're flipping the exponent fraction, it's that you're saying, what is the base? And I need to do the reciprocal of that. If it's in the numerator, it's now in the denominator, and the exponent becomes positive. Okay, let's do another example of one of those because I think it's very important that we see it again. So if I see this negative in the exponent, I'm thinking I have to flip this or do the reciprocal. It is equal to 1 over, I'm going to do 5x in brackets. I'm keeping this in brackets because I haven't dealt with any exponent yet. 1 over 2. We've taken a negative exponent, written the reciprocal of the base, and then made the exponent positive. Now we can convert this and say this is equal to 1 over, we're going to put a radical, our 5x, and now I assign my denominator as the outside piece, which now we know we don't actually have to put. If we know it's a square root is the one case where we don't have to write that number in the index. I mean, we could, but going forward in math, the further and further you go, it's not going to be written there. And this is written to the power of 1, which we could also write as 1 over the square of 5x, all to the power of 1. So if we wanted to write the power on the outside, that's fine. If we want to write the power directly connected to whatever's on the interior, that is also okay here. And to be correct, I should have brackets around my interior because that exponent applies to both. All right. Now, 17, I want to look at this one because this is really important. You are allowed a calculator in this unit. And so how I want you to utilize this is we need to figure out if I have an exponent of 1.5, well, what does that actually represent in terms of a rational number or something that can be written as a over b as integers? Well, 1.5, we can say this is equivalent of 1.5. And in our number sense unit, we knew 1.5. We can convert it by going 1 times 2 plus 1. That's 3 over 2. So now that we have a rational exponent, I go 6v raised to the 3 over 2. And now I can convert this from exponential into radical form by saying radical 6v in brackets, because I haven't applied any exponent to it quite yet, squared because the index value becomes our denominator. But remember, we don't have to write that. We know that if nothing's written there, it is a 2, and this is raised to the third power. Now this is also equal to bracket radical 6v bracket to the third power. That is an equivalent form of writing this. All right, now I just wanted to do some interesting examples right at the bottom of this page here, or page 24. 29, 30, and 31, and 32. These are all great examples to review, specifically because they can be thought about in a couple ways here. So in the first case, I'm going to think about x to the 6 with an exponent on the outside. This is telling me that I should technically do power rule because I have a power raised to another power here. I could do this by power rule and say 6 times a half, or x6 times 1/2. We know this is x to the power of 3. However, here's another way I could show this. What if I use exponential form and then I convert it to radicals and say this is equal to, well, square root or the radical of x6, and we know that if it's 2, we don't have to write it right in this position or the index position. Now I'm thinking, okay, if I want to perfectly square root this, how can I force the power of 6 to be a square instead? Well, I could break this apart and say I have x to the power of 3 raised to a power of 2. And by power rule, I know that 6 is equal to the 3 times 2 that I've separated here. But now here's the interesting property. I have a squared here, and I have a square root symbol. These undo each other. Therefore, my solution is x to the power of 3. So if I can force a perfect square or force my index value to be the same as my power, I can actually cancel those out and be left with the solution. Or I can do power rule here. Interesting, but if it asks you to do a specific method, you're going to have to do a specific method. Okay, let's go over to 30 here. I'm going to start by solving this using the radical form. So this is going to be equal to, I'm going to convert this into a radical by saying everything in my brackets is going to be together under the radical. This is raised to a 1/2, meaning my index value is 2 and my exponent is 1. Well, if my index is 2, I don't need to write it here. And if my exponent is 1, anything to the 1 is just itself. And so now I'm thinking, can I break these both apart into something that is squared that can cancel with the square root? Meaning, if I have this, what number squared represents 9? It's 3 squared. What number n? What can n be raised to that makes 4 in terms of a square? Well, n squared raised to the second power, 4 is equal to, by power rule, the 2 times 2. But here's where I've forced something. The square root on the outside is now can be canceled with the square here and the square here, meaning these all cancel. What is my remaining solution? 3 times n squared, which is just equal to 3n squared. So if I can force my index to be like my power on the interior, they can cancel directly. Now let's show that one more time here. I have 81 m6 to the 1/2. Actually, what we can do here first is I actually want to go to our, no, we'll do 32 first. I think this might be a better one to work with. So this is equal to, well, if I convert this into a radical, I have radical symbol 81, m to the 6th power. We know that the index here is the index here. Squared doesn't have to be written, and anything to the power of 1 is just itself, so that doesn't have to be written. And now this is equal to, I want to force the interior of my radical here to be replicate squares. What number makes 81 when squared? It is 9 squared. Then I do m. What number of m when squared gives you 6? It's m3 raised to the power of 2. Because if we have 3 times 2, that will give me that 6. But this 2 on the outside is going to be what allows me to cancel the squares all within the interior. Therefore, this is equal to 9m cubed. All right, one last example here. They try and throw in a trick here, but we're going to try and avoid that trick. They say, what if we give you a negative rational exponent? Remember, a negative rational exponent does not make this 6 over 1 positive. It's not that it's flipping the exponent, it's that it's flipping whatever's in the base here. So this is going to be equal to 1 over, all in brackets, 64 n12 bracket positive 1 over 6. Now, from our previous problems, we have this equal to 1 over, I'm going to set up my radical, so everything in the brackets is in my radical, 64 n to the 12. And then now we need to assign this index of 6 to the outside of my radical here. So this becomes 6th root of 64 n 12. And now, here's where we need to match up our index to the power on the interior of the brackets. 1 over, and we do the 6th root. Well, what number, when it's raised to the power of 6, will give us 64? It's actually 2 to the power of 6. What number of n, when raised to the power of 6, will give us 12? It's n squared raised to the power of 6 will give us 12. We know this because by power rule, 2 times 6 is equal to 12. Now, the nice piece about this is that we have a 6th root, a 6th power, and a 6th power. All of these can cancel. The 6th root undoes any 6th power on the interior. Therefore, our solution is 1 over 2n squared. So we want to try and force the index value to replicate whatever is on the interior, or I should say that vice versa. We want to try and force everything under the radical to replicate our index, because if everything replicates the index under the radical, we can cancel those powers and we're left with our solution once we've made those cancellations. All right, here's where your solutions are. So we did a bit of the homework there. I thought it was really important to just see some of those examples, but here's all your solutions. Get to practicing. You got lots more to do on this page here.